So hi everyone. My name is Darren Croton, and I'm a professor at Swinburne University. So we've been running our regular online ANITA lectures for the astronomy community here in Australia and around the world. I just wanted to say thank you all for your support. Today it's my great pleasure to have d.parkinson from the University of Queensland speaking, with all the interest recently in the BICEP2 results and the gravitational wave background in the early universe. It's very timely that he gives us some insight into these results. And so without further ado, I'll hand it over to David up at the University of Queensland. Thanks, David.
Okay, thanks very much for that introduction, Darren. So yes, as Darren said, in this talk I will be summarizing the theory of cosmological inflation, so describing where it comes from, how it works, what kind of observational predictions that it makes, and indeed where it stands in light of current data from CMB experiments such as Planck and BICEP. So this is a brief outline of my talk. Firstly, I'm going to be talking about how inflation proceeds. It's the accelerated expansion of the universe, but I'll go into a bit more detail of the driving mechanism behind it. And then briefly talk about how much inflation is necessary and what introduced the idea of the slow roll parameters. In the second section, I'm going to discuss the generation of density perturbations. So these are generated from quantum fluctuations in space-time, which are then amplified by the mechanism of inflation and turned into curvature or gravitational perturbations. And then I'll also be talking about the gravitational waves, which are predicted to be generated by inflation, and the idea of a consistency relation between the observables. And then finally, I'm going to discuss how inflation stands in light of recent data, especially from BICEP. So section one is looking at inflation from a sort of dynamical standpoint, looking at the accelerated expansion of the universe. So going back in history, cosmological inflation in brief is a period of accelerated expansion that took place in the very early universe. So it was proposed back at the beginning of 1980 by Alan Guth in that picture there, and others at the same time. A lot of people were thinking about the origins of structure in space-time and also the idea of an accelerated expansion. So we're really looking at the timescales of about 10 to the minus 34 through to 10 to the minus 32 seconds after the Big Bang. This is long before the creation of the CMB, which we see today, long before the creation of the primordial elemental abundances by nucleosynthesis that take place in the first 3 minutes, long before even the particles such as protons and neutrons freeze out of the quark-gluon soup. This is very back at the very highest possible energies. And it was posited there to solve three fundamental problems with the standard Big Bang model as proposed at the time, which I'll go into in a bit more detail. These problems are the horizon problem, the flatness problem, and the unwanted relic problem. So in brief, using this diagram, we observe the universe today on a light cone. We observe light looking back because light travels at a finite velocity. As we look back in time, as we look away from us, we're looking further and further back in time until we reach the cosmic microwave background. So the cosmic microwave background is the relic radiation left over from the Big Bang, and it represents a kind of as far back as we can see using only light. It's a bit like if we look at the sun, we can't see the center of the sun, but we can see the outside of the sun, the photosphere. So in this way, the cosmic microwave background is the photosphere for the Big Bang, except the radiation appears to us today as microwaves rather than light because it's redshifted by the expansion of the universe. But if we look back at the CMB sky on one side of the universe and the other, and it's pretty uniform in temperature. It's 2.7 Kelvin above absolute zero, but the variations are very small, only 1 part in 100,000. And given the standard model of the Big Bang, there's simply no mechanism to generate this uniformity of temperature. the horizon that the last scattering surface sees is actually very small. If you imagine these as causally distinct hot areas, there's no mechanism to thermalize them, to transfer information from one side of the universe to another in time for the universe to thermalize before the CMB is emitted. So this is known as the horizon problem. Literally, the horizon is too small for the universe to thermalize as we see it today. The second problem is the flatness problem. As we know, the Freidmann equation contains some large-scale homogeneous curvature, which we often call K. So if K is positive, the universe is positively curved, and like a sphere or ellipsoid. If K is negative, the universe is negatively curved, as you see, as in a hyperboloid. And if K is 0, the universe is flat. That is, the angles of a triangle add up to 180 degrees. The parallel lines stay parallel over all time. But if you have a universe which is expanding, but with negative curvature, what happens is that with negative acceleration, that is, a slowly decelerating universe filled with matter or filled with radiation, that this curvature will grow. Simply put, the density of matter or the density of radiation will diminish far faster than the curvature term. So if we look at the Freidmann equation there, relating the Hubble parameter, that is the rate of expansion, it's related to the density of matter, rho, and the curvature. And you can see that curvature goes as 1 over the scale factor a squared, whereas rho for matter will go as 1 over a cubed, and for radiation as 1 over a to the 4. But the universe, as we observe it today, is flat, or very, very close to flat. And this is dynamically unstable because as we wind the universe back in time, in order for this to be true, it would have to be even more flat, as in even closer to pure geometric flatness than we see today. And so if we wind it all the way back to deep into the radiation-dominated era, sort of 10 to the minus 32 seconds as the kind of inflation timescale, this requires fine-tuning of an order of 1 part in 10 to the 64, basically. It would have to be so flat to be dynamically unstable. It's a bit like trying to walk the tightrope. Here we have a picture of a man walking on the tightrope across Niagara Falls. It's a dynamically unstable situation. If he moves left or right, he will probably tumble to his death. But he has a self-governing mechanism. We need, in some ways, a self-governing mechanism to deal with the flatness problem. So finally, we have the unwanted Relic problem. So this is to do with spontaneous symmetry breaking. If we have some field in the universe, at high energy, it might have a simple quadratic potential, but then as the universe cools, it may fall into a minimum which is separated from 0. So at high energy, the field tends towards 0, but at low energy, it can fall into a positive or a negative well. If you imagine some kind of Mexican hat, it falls down from the peak of the hat into the brim. And so topological defects are generated when different regions of the space find themselves at different minimum. And the topological defects, such as the cosmic string or the magnetic monopole or the domain wall, are simply the boundaries between these two regions in space. And so the problem with this is that these things have a tendency to scale at the same rate as matter. And so if they're generated in very large numbers in the early universe, they should be around today in very large numbers. We should see their effect in the universe, in the formation of structure, etc. But we see not at all. There are no detected cosmic strings or magnetic monopoles out there. As far as we can tell, the universe has no topological defects. So we also need a mechanism to get rid of these things. So the proposed solution was a period of accelerated expansion in the universe, where the second derivative of the scale factor A is greater than 0. This solves the three problems simply. It dilutes the Relic density of topological defects such as strings and monopoles to be vanishingly small, effectively pushing them so away from us and to be practically beyond our horizon. It also pushes the density ratio omega, that is the ratio of the density of all material objects, back towards unity. so acting as a self-governing mechanism to push the universe back towards flatness. And finally, it decreases the Hubble horizon, such that the observable universe arises from a very small thermal patch. So it basically finds a small thermal patch and expands it such that the universe appears to be thermalized today. But in order to generate an accelerated expansion, we need something very strange. So if we look at the second derivative, the equation that covers the second derivative of the scale factor, the accelerational Ray-Choudhury equation, we see that in order for that to be the case, we have to have the sum of the density rho and the pressure P inside the brackets to be negative to counteract the negative. Oops, sorry, hold on. Oh, I just having some squeeze problems here. Just give me a second. To counteract the negative term at the front of the Ray-Choudhury equation. And so in order to generate an accelerating universe, we basically need the pressure of the thing driving the acceleration to be less than the negative of the density. In other words, we need some, negative 1/3 of density. We need some material or some force which has some negative pressure. And we often parameterize that through the equation of state. So W, which is just the ratio of, excuse me, of the pressure to density to be less than -1/3. So inflation is the mechanism to generate the accelerated expansion. And the simplest models of inflation posit a single, minimally coupled scalar field, which they call the inflaton, rolling down its potential. So here we have two models of inflation on the right-hand side. The first is sometimes called large field inflation, where it starts at some large value of phi and rolls in the direction given by the arrow down towards the minima at phi equals 0. The second model, which is sometimes called hilltop or small field inflation, where it starts at some very small value of phi, close to 0, and then slowly rolls away from 0 down towards the minimum at some value of phi, some finite value of phi. In each of these cases, we can generate inflation if the field is potential dominated. So the equation of state W, which is the ratio of the pressure to density, is phi dot squared minus V over phi dot squared plus V. I realize I've left off squared on that phi dot equation. I'll correct that on the slides anyway. The point here, though, is that for an accelerating universe where W is less than -1/3, we need the whole fraction to be negative. And to do that, we take the denominator and we make sure that V is greater than phi dot squared over 2. That is, that the potential dominates over the kinetic term. The potential V dominates over the kinetic term. So what is a scalar field? I've introduced these things called scalar fields, but unless you're a particle physicist, you may not be so intimately familiar with them. So technically, a scalar field is a spin-zero gauge boson. And the classic example which is used is the Higgs field, which gives rise to mass through the symmetry breaking Higgs mechanism. But in fact, we don't expect necessarily the Higgs to be responsible for inflation. In fact, there are lots of reasons to argue why it couldn't be. Instead, we're positing some extra field, which we just call the inflaton, which we haven't yet observed in nature. But what is it? How does it work? Well, the analogy that I would make would be some furnace. The heat experienced, say, by the bar in the furnace only depends on one parameter, the temperature. You can measure the temperature at different points in the furnace, but there's no vector component to the temperature. If you wanted to talk about more heat coming from a certain direction, you could talk about temperature gradients, but anything else, you're forced to go to a more complex description of a radiation field. In the same way, the scalar field is only dependent on its value at that point in space-time. Another analogy would be an electrostatic field, where you don't have any changes with time, Here, the electric potential in space only depends on one parameter, which is the field value. For a more complex description involving changes with time and magnetic fields, etc., then you're moving towards a vector description of electromagnetism. But if you consider only a completely electrostatic system, then the equations that govern the electrostatic field are very similar to those that govern the scalar field. Basically, my answer to the question, what is a scalar field, is just the scalar field is anything that obeys the Klein-Gordon equation, which I'm going to introduce in a moment. So, having introduced some mechanism to drive inflation, to drive the accelerated expansion, how long then does the inflationary period have to last to solve the problems, to solve the horizon problem, to solve the flatness problem, and to solve the unwanted relic problem? So normally in inflation literature we define this thing called n, which is the number of e-folds, such that n is the log of the scale factor at the beginning of inflation, the log of the scale factor at the end of inflation divided by the log of the scale factor at the beginning of inflation, and that's log base e. So it's basically the number of times that the universe is expanded by a factor e. So to be close to flatness today, the density parameter, for example, to solve the flatness problem, the density parameter -1 has to be close to 10 to the minus 60, up at the point where the universe has a temperature of 10 to the 19 GeV. So if we assume that the density parameter was of order 1, so there was some large curvature at the beginning of inflation, and then through the accelerated expansion we have that the Hubble parameter is roughly constant, we require roughly 70 e-folds. And normally you get about the same number for the horizon problem and the same number for the unwanted relic problem. Between 60 and 70 e-folds is normally seen as about the right amount of inflation. So inflation actually has to last for quite some time. You can't just have a brief burst of inflation and then solve all the problems. It actually has to inflate the universe by a factor of e to the 60 or e to the 70. So now we get on to the equations of motion that govern the inflating universe. So we have the Freidmann equation, where I've neglected the curvature term because it becomes subdominant very quickly. And we have the Klein-Gordon equation, which I spoke of earlier, which just governs the dynamics of the scalar field phi. And basically, it doesn't matter what else you have at the beginning of inflation. If the field is potential dominated and the equation of state is close to -1, the energy density of the scalar field will come to dominate very quickly. And so, as I said, to generate enough inflation, we need this to be the case. We need the universe to be accelerating a roughly constant density in the field for at least 70 e-folds. So at this point, we try and solve things analytically, and we make a couple of assumptions. And the assumptions we make simply are that the energy density, first off, of the scalar field is simply, rho is simply the potential V. So h squared, the rate of change of the scale factor divided with time divided by the scale factor, is equal to 8 pi g, the usual gravitational coupling, times the potential. But in order for this to be true, in order for the field to remain potential dominated, the field must evolve very slowly with respect to the Hubble timescale. So if I go back, as you can see, the Klein-Gordon equation looks kind of like a standard oscillator equation. You have the second derivative of the field, and then the first derivative times the Hubble parameter, and then you have the potential derivative with respect to the field. So if the field is evolving very slowly, then the second derivative of the field with respect to time, phi double dot, is going to be much less than the first derivative times the Hubble parameter. So then the Klein-Gordon equation simply becomes 3h phi dot equal to minus dv by d phi. So in order to maintain these conditions, we have these two slow roll parameters, epsilon, which is a function of phi, and it's simply v prime over v all squared with some extra term at the front relating to g, and we have eta, which is v double prime That is the second derivative of the potential with respect to the field divided by the potential. So in order to maintain inflation, we need both of these things to hold. So it turns out that epsilon is the thing that governs the dynamics, and as long as epsilon is small, we remain potential dominated, the universe continues to accelerate, and as long as eta remains small, then the field doesn't evolve very fast, and so we're not going to move out of this potential dominated regime. So these two parameters, epsilon and eta, will become important later when I start to talk about the formation of structure. And so we also require inflation to end after the required number of e-folds. So n is just the ratio, the log of the ratio of the scale factors, which just turns out to be the integration of the Hubble parameter with respect to time. And if we assume that the Hubble parameter is potential dominated, then we have our final equation of the number of e-folds in terms of the amount that the field moves between its initial point when inflation starts and its final point when inflation ends. And so inflation simply ends when the scalar field has evolved enough to be no longer potential dominated. So this will violate the slow roll conditions, and when the slow roll parameters will reach order unity. So as you can see from this, the amount of inflation is related to the first slow roll parameter. And for any given potential, if we know what v and v prime and v double prime, etc. are, we can calculate how far the field has to roll to evolve in order to generate the required numbers of e-folds. So I'll just go through a quick example case, which is a quadratic potential. This is sometimes called chaotic inflation. The idea here is that you start with some thermal bath, and then by chance the field is pushed up to some large value and then starts rolling down under slow roll conditions, which then kicks inflation off, and then inflation, just by random chance, happens to be enough to give rise to the universe as we see today. So in different regions of space you might generate less or more e-folds of inflation, but it just turns out that we happen to live in a universe where we had enough inflation to satisfy the observational constraints. So here it turns out that for this potential, and this potential alone, the slow roll parameters eta and epsilon are identical. And it simply relates to the value of the field. So when the value of the field becomes very small at the end of inflation, the slow roll parameter will start to become large. But the total amount of inflation is, we can then work out from the equation on the previous slide, and it turns out to be, so we have v over v prime, so the first derivative is just m squared phi, so the m squares cancel, and you're just left with the number of e-folds related to the value of the field at the beginning squared minus the value of the field at the end squared, which we're going to assume to be 0. So to get 70 e-folds, oh no, sorry, not 0, but the value that the field has to violate the slow roll conditions. So just to be very small. So to get 70 e-folds, the initial value of the field has to be 1 over root g, but as particle physicists, we almost never talk in terms of g. Instead, we talk in terms of the thing which is the inverse of g, which is known as the Planck mass, which is a very high energy condition. So to get 70 e-folds, the initial value of the field has to be very, very high energy indeed. Okay, so that's from a dynamical point of view. I'm now going to talk about the generation of density perturbations. So this is the sort of brief overview that everybody talks about. As well as solving the horizon, flatness, and Relic density problem, inflation generically generates structure of the universe, macroscopic structure. So everything we see, galaxies, clusters of galaxies, filaments, etc., all of this was seeded by some initial conditions. And inflation generates these initial conditions from quantum fluctuations. Quantum fluctuations are just random oscillators in the zero state, in the vacuum state, but are then amplified by the expansion of the universe, by the accelerated expansion of the universe, and being stretched beyond the horizon, when they then become macroscopic or classical perturbations. So what do I mean by all of this? Well, let me try and give you some kind of explanation. Here I have a plot of time on log time on the x-axis versus some physical scale. So in cosmology we often don't think of physical scale, we think of some co-moving scale, but let's imagine we have some physical object. So the physical scale here will just grow as A, the size of the universe, whereas by the scale factor, whereas the Hubble length will be 1 over h. And in the accelerating universe, the potential dominated acceleration universe, h will go very quickly to a constant and will only evolve very slowly. So when inflation starts at the first dashed line, then the Hubble parameter basically goes to a constant and the physical Hubble length goes to a constant. And so some physical thing, which is growing with the expansion of the universe, will suddenly become very large. And it could in fact become larger than the Hubble length. So imagine you have two particles which are separated by some standard co-moving length. They can be sort of two galaxies moving apart, for example. When the acceleration kicks off, they will very, very quickly be ripped apart effectively. And in fact, because inflation really is an anti-gravity force similar to the dark energy, there really is a force acting to push these two particles apart. If I then turn it into some co-moving length scale, so we understand a little bit better what's going on. So here I still have log time on the x-axis, but now on the y-axis I have co-moving scale. So the co-moving separation of two objects here will be a constant, but the co-moving Hubble length, which is 1 over AH, will rapidly decrease during inflation because h is a constant, whereas a will be increasing very quickly. And so if you had some system, say two particles bound together, not particles bound together, but it works with those as well, but we just consider two co-moving systems like two galaxies or just two atoms of dust drifting apart, then very quickly they will find themselves outside the Hubble horizon. So this is what happens to the quantum fluctuations as well. You have a quantum fluctuation, which is just a vacuum state oscillator. There's a very simple equation for its amplitude. You can work it out pretty easily in second-year quantum mechanics. But then what will happen is that it will just be oscillating as it goes along, given its frequency given by the co-moving separation, the bounds, if you will, of the vacuum state. And then when that size becomes less than the Hubble horizon, it basically becomes causally disconnected. There's no way that it can oscillate anymore, and it becomes frozen. So the way that's commonly described in the literature is that you can imagine this as the quantum oscillator as virtual particles being created and destroyed, a virtual positron and a virtual electron springing into existence, maintain zero charge, but over some very small time scale, some quantum foam, if you like, if you want to use that term. They exist, and then they annihilate and go back to nothing. They're virtual particles, so they don't have any long-term existence, except during the accelerating universe, when the separation between them is suddenly smaller than the Hubble length. They're effectively now causally disconnected. So you've generated some quantum oscillator, but you've taken the two parts of the oscillator and you've causally disconnected them. So they now exist as macroscopic fluctuations. There's no way they can return to the ground state again. They are actual fluctuations in space-time. So just to go through this idea again, inside the horizon, when the wave number is greater than AH, remember the wave number is 1 over wavelength. So this is for very small wavelengths. The flat space-time solution to the quantum oscillator holds. You just have rapidly oscillating quantum fluctuations. But outside the horizon, when k is now less than AH, the oscillation has become frozen in and cease oscillating. So we call this horizon exit. And you can see that if we had some oscillator given by the blue line, it would be oscillating nice and cleanly until it exits the horizon. When it becomes frozen in, it then becomes some fluctuation in space-time, and then it will just wait around for a long time until it then re-enters the horizon long after inflation ends, and then it can start evolving again depending on what's happened in the meantime. So the spectrum of quantum fluctuations, that is their amplitude as they exit the horizon, so evaluated when k equals ah, is just given by the Hubble parameter at that point. It's just h over 2 pi all squared. So the amount of boosting that these things get, the amount of amplification, is just simply related to the Hubble parameter at that point. But the other interesting thing about these oscillations is that they're random, so that if you consider one mode k and another mode k prime, their phases will be completely uncorrelated. So you can imagine this as the spatial positions at the minima and maxima. You might expect that for different wavelengths that the spatial positions of the maxima all line up. We see this in structure formation, for example, where you have a galaxy lying at the center of a cluster. So the galaxy is the small scale structure and the cluster is the slightly larger scale structure. There, the density of the galaxy and the density of the cluster line up in the same spatial position. Here, though, because the oscillators are random, they're just oscillating backwards and forwards until they exit the horizon, the spatial positions will be completely uncorrelated. And so inflation naturally generates what are called Gaussian random fields, uncorrelated Gaussian perturbation spectra. So I now need to go back from quantum mechanics to general relativity. Excuse me. So we decompose the metric. So if we had just the flat space-time FRW metric, all of these terms, phi, psi, and e, would be 0. We would just recover minus dt squared plus a squared with some space part. That's the standard flat FRW metric. But if we wanted to do perturbation theory, we would add some metric fluctuation on the time part, which we call the Newtonian potential phi. We have some metric fluctuation on the space part phi, and we have these traceless parts e. So you can imagine that you can think of the traceful part, the phi and psi, as just being the gravitational potential at that point. Simply, we sit in like on Earth, we sit in a gravitational potential. In the same way, we distribute gravitational potential through space-time with some spatial distribution and with some time evolution. But they're scalar quantities. They only depend on, the local matter density at that point. Whereas the traceless part, E, which is a traceless tensor of order 3 in 3 spatial dimensions, are tensor perturbations, which we interpret as gravitational waves. These are fluctuations of space-time traveling along. So these are traceless. They don't really depend at all on the local density. Rather, they are manifestations of fluctuations of space-time which propel themselves through the fabric. And so what we've done is we've started with some metric and we perturbed it, and then we've decomposed these metric potentials into the scalar part and the tensor part. You might also ask, are there vector perturbations? The answer is yes, but in general, these things have a tendency to decay away very rapidly, unless there is some mechanism driving them. So going back to topological defects like strings or magnetic monopoles, these things, or even things like magnetic fields, these things have a tendency to source vector perturbations. But in general inflation, even if you were to generate vector perturbations, they decay away too rapidly to be considered. So the power spectrum of curvature fluctuations is generated by the quantum fluctuations. So here I have what's called the comoving curvature perturbation R for a given wave number k, and this is generated by some quantum fluctuation delta phi with some pre-multiply, which is just simply related to the Hubble parameter divided by the time derivative of the scalar field. So the power spectrum of the curvature perturbation, the scalar power spectrum, is simply the power spectrum of the quantum fluctuations, that is h over 2 pi all squared, multiplied by the square of this pre-multiplier term. And so you can, and these are both evaluated at horizon exit, at when the wave number is equal to the scale factor A times the Hubble parameter H. So we can then go back and do the calculation and refer these to the potential parameters. You get something that looks like this thing at the bottom, where you just have the potential value divided by the slow roll parameter. And so we can evaluate the potential and we can evaluate the slow roll parameter epsilon at the point where the perturbation exits the horizon, and then build up a power spectrum from that, a power spectrum of scalar fluctuations. And the good thing about that, of course, is that we can compare that to observations. So on the right, I have a figure, quite a famous figure now, I think, taken from a paper by Max Tegmark et al. 2002. And here we have the power spectrum of scalar fluctuations. So in black, we have the power spectrum measured by the cosmic microwave background at that point. It's got a lot more accurate since then, I think. In green, we have the power spectrum measured by the galaxy power spectrum from 2DF, the 2DF Galaxy Redshift Survey. And then going down to smaller scales, so larger wave numbers here on the right-hand side, we have measurements from the abundances of clusters in blue, measurements from weak lensing in magenta, and from the Lyman alpha forest down to very small scales, indeed, in red. So all of these things are basically measuring the power spectrum of matter as we see it today. But of course, the power spectrum of matter should just be tracing out the power spectrum of scalar perturbations in the universe. Tensor perturbations will not generate structure. Matter has a tendency only to fall down the gravitational potentials, that is, the scalar perturbations. And so what we're directly probing here is the curvature, is the distribution of curvature perturbations in spacetime. So we normally parameterize this thing by some scale, by some power law. So the power spectrum of scalar perturbations P as a function of K is related to some power spectral index, ns minus 1. So if ns is equal to 1, we have what's called a scale invariant power spectrum, which is equal power on equal scales. If ns is greater than 1, we have what's called a blue tilted spectrum, because we'll have more power for larger k. The power will grow as k, and so for those very small wavelengths, those blue wavelengths, you'll have more power than on larger scales, the red wavelengths. And if ns is less than 1, you have what's called a red tilted spectrum, where you have more power on the large scales and less power on the small scales. And as you could see from my previous slide, we can evaluate the power spectrum of curvature perturbations in terms of the potential parameters. And so we can work out how these things change over inflation. And in fact, the spectral index is simply related to, through some simple formula, to the slow roll parameters epsilon and eta. So we related directly the distribution of scalar perturbations to these slow roll parameters that govern inflation. But furthermore, since the amplitude of the power spectrum should be related to the amplitude given from the potential, the value of the potential, we can directly measure the value of the potential, V, over here. Except there's a catch. You can't do it directly because there's this factor R. And R is the thing that I'm about to come to now, which is to do with the tensor perturbations. So I've talked through what I mean by a scale invariant power spectrum, but just to go over this again, the amplitude of the scalar perturbations is determined by the Hubble parameter at Hubble horizon exit. Because it's evolving very slowly, each perturbation receives roughly the same amount of amplification, but not exactly. If the Hubble parameter really was exactly constituting inflation, they'd each receive the same amount of boost, but they don't. And so you have ns minus 1 being very slightly different from 0. And all structure we see in the universe today actually comes from the very beginning of inflation, from the first 10 or so e-folds. Because these things are the things which re-enter the horizon at the latest time. So actually, all the modes if I go back to this picture of the scalar perturbation spectrum, all the modes on the left-hand side, probed only by the cosmic microwave background at the moment, are those modes which re-entered the horizon, which have not actually re-entered the horizon, which haven't evolved. And everything on the right-hand side are those modes which have by now re-entered the horizon and gone on to evolve and generate things like baryon acoustic oscillations and nonlinear structure. So the tensor perturbation power spectrum, the more important thing which people are probably listening to this talk to get some kind of a handle about and some idea about, are propagators gravitational waves. So here I have the equation of here I have the equation of motion of h, where h is simply the amplitude of the gravitational wave, and the gravitational wave has two polarization states, the cross and the diagonal state, the orthogonal and the perpendicular. And you'll notice that the equation of motion isn't sourced by anything. You have the second derivative, you have the first derivative multiplied by the Hubble time, you have this term relating to the size of the perturbation, but you have nothing relating to the matter. There's no source term generating it. And that's because that once the gravitational wave is off, that's it. It basically self-propagates it. It doesn't require a continual source to generate it. And so this is actually the same as the equation of motion for a massless scalar field. And so it turns out the resulting power spectrum is very, very similar to our scalar fluctuations our quantum fluctuations. And so we have a power spectrum of gravitational waves, which is just h over 2 pi squared, evaluated at horizon exit. And we have a spectral index, n, which is -2 times epsilon. So you notice that we have 4 observables, basically. We have the amplitude of the primordial gravitational wave spectrum. We have the spectral index of the primordial gravitational wave spectrum. And then going back, we also have the amplitude of the scalar perturbation spectrum and the spectral index. So we have 2 amplitudes and 2 spectral indices. But in fact, our slow roll parameters were defined only in terms of 3 components: the potential, its derivative, and its curvature. So we can define our entire inflation model just in terms of these 3 functions, and we measure 4 quantities. It should be apparent then that if you have more observables than you have quantities that you're trying to measure, there should be some consistency relation between the observables. So here again are the 4 parameters that I'm trying to measure: AS, NS, AT, and NT. And inflation predicts a consistency relation between 2 of these quantities, or rather between 3 of them, which is the ratio of AT, the amplitude of the tensor perturbations, divided by AS, the amplitude of the scalar perturbations, is equal to -8 or -6.2 or -0.5, depending on how you define the tensor perturbation power spectrum and the scalar perturbation spectrum. But it's always the negative of the spectral index of the tensor perturbation. And inflation exactly predicts this consistency relation between the 2 power spectrum. And so we don't normally talk about measuring the amplitude of the spectrum of the tensors or the spectral index of the tensors. We only talk of this R, this relationship between the amplitudes. So now I will go on to talk about recent results. So if we run it back to the Planck results, so here I have a figure from the Planck paper, results are constraints on inflation. And here I have the constraints on the spectral index on the x-axis and the tensor-to-scalar ratio on the y-axis. And here are the results from the Planck team combining their temperature power spectrum with polarization from the WMAP team and baryon acoustic oscillation measurement from BOSS and 60F. So here we have a lambda CDF model, the standard 6 numbers, but with the addition of R, where R is our tensor-to-scalar ratio. And in blue, you can see that we have a 68% contour around 0.96, 0.97, going up to about 0.9, 0.8, 0.9, up at 68%, and going up to somewhere in the sort of 0.15 region, and 95%. So if we marginalize over NS, we basically end up with R being 0.11 and 95% limits from analysis of the Planck data. If we don't assume a power law spectrum of scalar perturbations, that is, if we allow the spectral index to change with K, which we hadn't really discussed up to this point, it's an extra parameter that which we call the running of the spectral index. Then the constraints become a bit looser because you've got a bit more freedom, and so you can have a value of R as high as 0.3. And this was the state of the art. It was the Planck temperature results plus the TE and E mode polarization from WMAP. And then March this year came along, and we all saw this paper. In fact, this figure. So these are all the results for the B mode polarization. So basically, the polarization of the CMB can be broken down into the grand free and curl free. And so the curl free is the E mode, and the grand free is the smaller signal, the B mode polarization. And all of these triangles represent 2 sigma upper limits on the B mode. So we have everything back to CatMap and the cosmic background interferometer and other acronyms that nobody can even remember these days, apart from if they were actually on the team. But the BICEP results, BICEP 2 in fact, so BICEP 1 are these grey constraints, whereas BICEP 2 were this detection of the B mode. So the B modes can only be generated in 2 ways. They can be generated by lensing of E mode polarization, which gets you this very large multiple of very small scale peak over here, but they are also generated by primordial gravitational waves, which is this dashed curve rising and falling at around L of 200. And so these measurements of B mode polarization indicated that we'd found it. We'd found the primordial gravitational wave power spectrum from inflation. And indeed, we can then go back to our equation for the amplitude of the scalar fluctuations, insert our value of R into here, and get a value out for the potential, for the energy scale at which inflation is taking place. We get a value of 2 times 10 to the 16 giga-electron volts, far, far in excess of anything that we can measure at the Large Hadron Collider. This is grand unification scale. Inflation would be a phenomena of the highest possible energy physics. And we can also use our minimum 70 eVolts and our measurement of the spectra of the tensor-to-scalar ratio of 0.2 to determine that the mass of the field, how far the mass of the field has moved. As you remember, how much inflation is given by how far the field travels from initial point to final point. And we find that the field has to have rolled by about 10 times the Planck mass. So for the first time, we've actually measured the energy scales of inflation. We've seen how far the field has measured. And this is because the tensor perturbations, the primordial gravitational waves, give us a direct measurement. They come to us directly from inflation. You don't have to wait around for the scalar perturbations for structure to fall into them, for gravitational potentials to form, for galaxies to form. For all these things, you have to wait 13.8 billion years for the universe to cook. You just put your thing, you watch the polarization pattern, you put your satellite at the South Pole, you put it in the sky, you wait for the polarization pattern to form, and then you measure them directly. Now, we haven't actually measured the gravitational waves directly themselves. Up until now, I believe no gravitational wave has been directly measured on Earth, but we're measuring their imprint in the cosmic microwave background polarization. So, does this mean inflation is proven? Well, I would say no, or at least not yet. Although inflation generally does predict a power spectrum of tensor perturbations, we would need to measure both the amplitude ratio, R, the ratio of tensor to scalar perturbations, and the spectral index of the perturbations, NT, to confirm the consistency relation. Because if the consistency relation doesn't have the form that we'd expect, for example, if the spectrum, if I go back a few slides, you can see from here that the spectral index of the primordial gravitational waves is negative, meaning that they're always red tilted. If we found that we had a power spectrum of blue tilted gravitational waves, that would be something very different. And that couldn't be inflation, at least by no ordinary model. We also have the problem that the results are in tension with those from Planck. If you could see that unless you have something like an R of 0.2 is outside the standard 95% limit, though it is inside the 95% limit if you include a running or some strange power spectrum of scalar perturbations. And finally, there have been a few papers indicating that the dust modeling from BICEP 2 has not been done accurately. I refer you to the papers on the slide. So to conclude then, inflation is a theory that predicts a period of accelerated expansion in the very early universe. And this acceleration amplifies quantum fluctuations to macroscopic size and seeds the formation of the large-scale structure which we see in the cosmic microwave background and in the distribution of galaxies and clusters. It predicts a nearly scale-invariant spectrum of Gaussian density perturbations, which we have confirmed to be the case. And it also predicts a spectrum of primordial gravitational waves, which we have observed something that looks very like that from BICEP 2, implying a very high energy for the inflaton potential. And with that, I will finish. Thank you very much.
Okay, well, thank you for that. Thank you for that, David. Just to finish up, I'll just say David will be online for a little while, and you can post any questions you have about inflation or BICEP 2 in the chat box underneath the Google Plus post for this Hangout on Air. Also, refer you to ANITA, the ANITA webpage, anita.edu.au/lectures, where we host all our lectures. I want to say thanks again to David for presenting these results and and this information about inflation. And I'm sure that there's going to be a lot more discussion within the community as Planck releases its new results later in the year, and with a lot of other experiments measuring similar properties. So thanks again to David, and thank you to all of you for watching. Bye.